All right, hi everybody. Today we're going to be covering 3.1, which is focusing on atoms, the different parts of an atom, and how we can tell them apart. We're also going to get into how we discover the different parts of an atom. So make sure you have already turned in your Chapter 3 vocab. You should hopefully have a note packet by now, and let's get started. So again, chapter 3 is all about atoms and the building block of matter. So in chapters 1 and 2, we talked about chemical physical changes, changing of matter, and then we also got into a little bit about the density and the makeup of matter. So now we're going to focus purely on looking at just the atoms. So focusing on elements, and then how are we figuring out how many protons, neutrons, electrons, and things like that are inside of them. So 3.1, this is about how we have discovered the atom. So going all the way back to ancient Greece time, we are looking at Democritus. So he is between 460 to 370 BCE. He was a pupil of Laplace. He has elaborated on his idea of atomism. So the universe is composed of the basic indivisible particles turned atomos, translated into English later on into atoms. So he believed that there were these solid structures that we called atoms, and they worked together to be able to make up what we know as matter today. Well, Aristotle came in and 384 to 322 BCE, and he was a generation that succeeded Democritus, and he disagreed with atomism. So he did not agree that there was these tiny little things that make up atom or make up matter. He believed that matter was continuous, that a solid is a solid, and there's nothing that's separating it whatsoever. So at this time, we also believe there were only 4 essential elements. There was earth, fire, air, and water. So obviously, we have come a very long way since 400 BCE, but back then we believed that atoms were these tiny little things that built what we see every day. So we were able to come up with the particle theory of matter. Was supported as early as 400 BCE by the Greek thinkers such as Democritus. He called basic particles an atom based on the Greek word meaning indivisible, and this led to the 3 fundamental laws. So we're going to discuss those 3 laws kind of in depth on each one. So it kind of explained how matter behaves in a chemical reaction. So explaining how we're creating new things through a chemical reaction. So scientists in the late 1700s understood that substances combine to create new ones, which we now know as a chemical reaction. We just didn't understand how it happened. We knew that if you took bread dough and put it in the oven, it would turn into bread. We could see that happening in front of us. We could also see, putting something into fire would then burn and turn into ash, and it was no longer that object anymore. And so we could see those changes occurring. We just didn't understand on what level, what was happening, especially on the molecular level. So in the 1790s, the study of matter was changed by the emphasis on quantitative analysis of chemical reactions, which led to 3 laws. You are going to need to know these 3 laws for your test. So the first one, I would star it, highlight it, whatever you got to do to make sure you go back over it, is the law of conservation of mass. So it states that mass is neither created nor destroyed during an ordinary chemical reaction or physical change. So again, any sort of change, we are not going to lose matter. So matter is never created nor destroyed. It is just simply changed. If you have time, I highly recommend checking out this video. It does a great job of showing how even in a chemical reaction, a lot of times when we go through a chemical reaction, we will see a mass change, even though we know what goes in must come out. The reason for that is because we're not trapping the gas that is being formed. And so this lab, you actually cover up and you stop it with a rubber stopper, and the chemical reaction, all the gases are trapped. So it actually, the amount of matter it starts with, so that 390 or 369.1 grams, you have that at the very beginning, mix it together, let the chemical reaction take place, which this one actually will form a precipitate, and you'll see a color change and a precipitate, or it will get cloudy. So it tells you a chemical reaction is taking place. And we'll see we end with the exact same amount because what we start with is what we end with. Things do not just mysteriously appear, disappear. They always are there. So what you start with is what you end with through the law of conservation of mass. The next one I would highlight is the law of definite proportions. That's the fact that a chemical compound contains the same elements in exactly the same proportion by mass, regardless of the size of the sample or the source of the compound. So what that is trying to say is it doesn't matter where I get my source, it is going to stay the same every single time. So the composition will stay the same. So for example, each salt crystal seen to the left contains exactly 60.66% of chlorine and 39.34% sodium by mass. So it doesn't matter if I have 5 grams or 500 grams, each one of those salt crystals will be 39.34% sodium, 60.66% chlorine every single time. It also doesn't matter where I get that salt crystal from. I can get it from a mine in one place and a mine in another one, or make it in the lab. It is going to be the exact same every single time. So the chemical compound contains the same elements in exactly the same proportion by mass, regardless of the size of the sample or source of the compound. That is the law of definite proportions. And the last one is a law of multiple proportions. Again, I would highlight whatever you got to do to make sure you go back over this. If 2 or more different compounds are composed of the same 2 elements, then the ratio of the masses of the second element combined with the mass of the first element is always a ratio of the smallest whole number. So what that's saying there is basically if we're combining 2 elements into one compound in whatever ratio, it is always going to be in the smallest whole number possible. The reason for that is they don't love it when there are multiples when there doesn't need to be. So for example, if we're combining carbon and oxygen here, carbon will form, or carbon and oxygen can form carbon monoxide. It can also form carbon dioxide. But again, it's always in the smallest whole number possible. You will never see half of a carbon atom or half of an oxygen atom. It'll always be at a whole number. And again, we always want the smallest amount. Just trying to make life easy. Always go to the smallest amount as a whole number. Okay, we're also going to get into John Dalton. This is about 1808. He proposed an explanation that encompasses these 3 laws. So he came up with a way to kind of explain all of the earlier laws in kind of one explanation. So he called it his 5 postulates, known as Dalton's atomic theory. So all matter is composed of extremely small particles called atoms. That's number 1. 2 is elements are identical in size, mass, and other properties. 3, atoms cannot be subdivided, created, and destroyed. D, atoms of different elements combine in small whole number ratios to form compounds. And E, in chemical reactions, atoms are combined, separated, or rearranged. So for the most part, Dalton did a great job of explaining it. Now, was he perfect? No. There are a few things that we have then found out not to be true. But for the most part, for what he's throwing out there it's a great kind of encompassing of all those different laws that we were just discussing before. If you want a little bit more, here's Dalton's atomic theory as well. So you can go back, watch this video. Now, the few things that Dalton got wrong. So he said atoms of an element are identical in size, mass, and other particles or properties. That is not true. They can vary in mass. The reason they vary in mass is because of their isotopes. So an isotope is the same number of protons, but a different number of neutrons. And protons and neutrons are what create the mass behind an atom. And so since we look at different isotopes of the same element, their masses are going to be different. Now, it's not going to be dramatically different, but it can be a little bit different. So they are not identical in mass. Atoms cannot be subdivided, created, or destroyed. Atoms can be divided into smaller subatomic particles, which we know as protons, neutrons, and electrons. So generally, we don't break down atoms further, but we can break them down into their parts and look at them at a little bit deeper level. But all matter is composed of atoms, so he was correct on that. And atoms of one element have different properties within the atoms of other elements. So basically saying each element behaves differently from each other, no matter what type of element it is. Okay, so that's 3.1, kind of a little bit of the background. We're going to get into 3.2 today, or at least a little bit more. So that's talking more of the structure of the atom, and we're going to get into the different parts. So the first one is looking at the late 1800s, and we were doing what's known as the cathode ray tube experiment. So that's where the electric current is passing through a glass tube hooked up to a vacuum pump. So this is what it looks like over here on the left. And we were able to discover the electron by using this experiment because we saw this beam of light coming across. And we noticed that if we moved a magnet nearby, that it would actually cause the light beam to bend. And they're like, well, that's kind of weird that this light is now bending. Well, come to find out, that beam of light is a bunch of electrons. And it was the positive end or the negative end of a magnet. And again, two opposites will repel each other. And so it shoved the light beam downwards. And so we were able to then discover the electron. So we're going to watch this video. Kind of goes a little bit more in depth on it as well.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thomson, who became the director of the old Cavendish laboratory. In 1896, Thomson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates across which you can apply a voltage, and they hit the end of the bulb here on a screen which glows so you can see the beam. Now this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thomson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thomson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thomson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. It might apparently Shakespeare say, my use is great because I am so small.
The electron was the first discovery of a fundamental particle, and it is interesting to realize that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how did the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thomson's that proved him wrong.
Okay, so that's just a little bit of an intro into the electron. So yeah, J.J. Thomson gets the credit for discovering the electron using the cathode ray tube experiment. Okay, so we're going to stop there for today. We'll pick up here on Thursday. Make sure you're filling out your notes, getting everything ready. If you have any extra time, check in the campus, see what you're missing, and get caught up. If you have any questions, please let me know. Have a great rest of your day, and I will see you on Thursday.